Hello, and welcome to the Math 120 Final Exam Review, Exponentials. So this final review is based off of Doñana Community College Final Exam Review posted at dacc.nmsu.edu/math. On the right side menu you can find Final Reviews. When you click on that, you'll see a list of all the different final reviews. The numbers in these review problems come directly from that posted final review. My name's Tuesday J. Johnson. I'm a lecturer at the University of Texas, El Paso, and an assistant professor at Doñana Community College. Here we have an icon, the calculator with the banning of the calculator. So this is the no calculator section of the exam. The exam will come to you in two parts. On part A, you have no use of a calculator, and in part B, you're allowed the use of a calculator. Don't freak out. I know your calculator's a lot like a security blanket, but you're a big kid now. You won't need the calculator for most of these problems. I'm going to say for all the problems. If it says no calculator, you really don't need it. The numbers are nice, they work out. So let's start with number 9 here. Given f of x equals 3 to the x. I want to find the inverse function. Well, first thing we know is that logarithms were defined to be the inverse of an exponential function of the same base. We knew that exponential functions were 1 to 1. We knew that we could find the inverse. We run into problems when we try to find it algebraically. And so someone, in their wisdom, defined logarithms to take care of that for us. So anytime you see an exponential function, f of x equals 3 to the x, guaranteed the inverse is log base 3 of x. Part B, we're going to complete the column for f of x, then use our knowledge of inverses to complete the last two columns. Alright, my function is 3 to the x. When x is negative 1, 3 to the negative 1 is 1/3, right? That negative 1 says the reciprocal. The reciprocal of 3 is 1/3. When x is 0, 3 to the 0 power is 1. 3 to the first power, 3 to the 1 is 3. And it's at this point, I could keep evaluating, right? 3 squared is 9, 3 cubed is 27. But notice, the base multiplier is 3. Once I know the y-intercept, I can multiply by 3 to get the next value of y going up. I could divide by 3 to get the previous value of y if I'm going down in x values. So in this way, I'm able to find the y values, the f of x values, for a given function with the set x values we're given. Now, we want to use our knowledge of inverses to complete the last two columns. So these three columns will all be blank, and you'll need to fill them in. What does an inverse do? An inverse switches x and y. So what was an x becomes a y. What was a y becomes an x. So the pairs of points that you have in these two columns get flipped around for these two columns. That's it. That is all you're going to do in order to find an inverse. You don't even have to have an equation for it. What was an x becomes a y. What was a y becomes an x. So we just flip those around. Now, I want to sketch f of x and its inverse on the same set of axes, and I'm going to include the line y equals x, because we know a function and its inverse graphically are symmetric across the line y equals x, and I can kind of get a better idea of what it might look like. I cheated. I used Desmos.com to put this graph down because it's a lot easier for you to find instead of my shaky little hand drawing graphs. But all I did is plot the points. When x is negative 1, y value is a 1/3. When x value is 0, y is 1. X is 1, y is 3, and so on. And you can see here in green, the graph of the inverse is indeed the graph of a logarithmic function. And so there we go. Log base 3 of x is the inverse of 3 to the x. We can fill in our table of values. Inverse, we just switch x and y's. Once we have some points, you can all plot a graph. Good work. So let's try it again. Given f of x equals 4 to the x, we know our inverse will be the logarithm of the same base. So the inverse is log base 4 of x. When x is negative 1, 4 to the negative 1 is 1/4. 4 to the 0 is 1. 4 to the first power is 4. 4 squared is 16. And 4 to the third power is 64. I know it says no calculator, but you can do it, I promise. We know that all an inverse does is switch x and y, so we had negative 1 1/4, now we'll have 1/4 comma negative 1. 0 1 becomes 1 0, and so on. Once you have your table of values all filled in, I can graph f of x. Notice that's a little steeper than our last one. And I can graph f inverse of x on the same axis along with the line y equals x. Graphing exponential functions, very straightforward. Graphing log functions, very straightforward if you have the corresponding exponential function. Don't let it be hard. Don't get all, oh, how do I graph a log? No, you graph a log by remembering the inverse property. What was an x becomes a y. What was a y becomes an x. So let's evaluate some exponential functions. We're going to let f of x be 16 to the x. I want to find f of 0. Okay, notice f of 0. So the x is replaced by a 0 on the left. Let's replace x by 0 on the right. F of 0 is 16 to the 0 power. Anything other than 0, or infinity, raised to the 0 power is 1. So my answer is 1. F of negative 1. I want to evaluate when x is negative 1. I get 16 to the negative 1. Negative 1 power, that's reciprocal, so I'll take that to the denominator. That's 1 over 16. This is a no calculator problem, so I don't want to see any decimals there. Just let it be easy. Let it be straightforward. Negative 1 power, reciprocal, flip 16 over, and you get 1/16. If you want to find f of 1/2, all right, now the 1/2 is our input. The 1/2 is in our exponent. 16 to the 1/2 power. Remember, rational exponents. The denominator becomes the index of our radical. 1/2, the 2, that's a square root. You know the square root of 16 is 4, and that's our answer. Do not make this more difficult than it actually is. Find the inverse of g of x equals 6 to the x, as we talked about on the 2 previous slides. The inverse of the basic exponential function with base 6 is the logarithmic function with base 6. So I would write it as g inverse, because my function's name is g, got to keep the name straight. G inverse of x is log base 6 of x. You could use the change of base formula. There are some textbooks that show natural log of natural log of x over the natural log of 6 is the inverse. I don't like this. It's the log base 6 of x. There are calculators now that can evaluate logarithms with various bases. We don't have to use the change of base formula anymore. If you remember this property, you're doing great. Good work. Notice, this time I mean it. There's no calculator icon here, which means you get to use a calculator. Suppose the newest version of your favorite smartphone comes out today. Assume that a total of 30 people go to your local cell phone dealer to purchase this phone today, and that each day the total number of people who purchase the smartphone doubles. Let S of t represent the number of people who have purchased the smartphone t days since today. We want to find an equation for S of t. Now, how do we know what type of equation? When I look right here, let me find where it is. There we go. The number of people who purchased a smartphone doubles. When it doubles, it indicates multiplication. So if we're multiplying each time, what multiplies? Oh, the base multiplier multiplies. So we know this is going to be an exponential function. An exponential function, S of t, equals, the a value is going to be how many people have it on day 1. 30 people start with the phone. Doubles indicates a base multiplier of 2, and I want to make sure I use the correct variable, t. So S of t equals 30 times 2 to the t. So after the first day there's 30, second day there's 60, then 120, then 240, and it keeps going from there. According to S of t, how many people have purchased the smartphone 7 days from today? Well, 7 days later, the 30 that started will have doubled 7 times. 3,840 people have purchased the smartphone after a week. That seems kind of low, but we're looking at a small town, not necessarily a global, nationwide, even statewide sales of the smartphone. But you have to have the equation right in order to get the estimate right. So remember, it doubles. It doubles, that indicates multiplication. A problem that indicates multiplication by the same thing over and over again, that's going to be exponential, because the exponential function has a base multiplier. So let's try it again. Suppose a flu epidemic has broken out in all Math 120 courses at your school. Assume a total of 9 people have the flu as of today, and that each day the total number of people who have the flu triples. Let f of t represent the number of people who have the flu t days since today. We want to find an equation for f of t. Okay, the number of people who have the flu triples. We don't add 3 each time. We multiply by 3. Since the flu triples, it indicates repeated multiplication, which leads us to think in terms of exponential functions. 9 people have the flu today, so 9 is our starting value. The number of people that have the flu triples, so our base multiplier is 3. We're multiplying by 3 each time. And since it is repeated multiplication by 3, the exponent is t. I'm not multiplying by t, the exponent is t. According to our function here, how many people at your school will have the flu 4 days from now? That's evaluating f of 4. So that's 9 times 3 to the 4th power. I'm going to use my calculator on that. A 3 to the 4th power happens to be 81. 81 times 9, 729 people will have the flu after 4 days. This is why when you have the flu, you don't come to school. Don't come to school when you have the flu. I don't know how many different ways I can say it. Please don't make me sick. Statistics indicate that the world population since World War II has been growing exponentially. If we assume exponential growth, the world population can be modeled by this equation. So P of t equals 4 times 1.019 to the t power, where P of t is the world population in billions, and t is the time in years since 1975. Now, remember, model real-world situations, not necessarily accurately for an extended period of time. They have differences here and there, but we're going to go with this model. We're going to estimate the world population in 2015. Well, in order to do that, we're not just going to put 2015 in here for t, because t is the time in years since 1975. 1975 plus 25 years takes us to 2000. Add another 15 years, 25 and 15 makes 40 years later. So I actually want to find the population 40 years after 1975. And I'm going to put that in my calculator for parentheses 1.019 close parentheses to the power of 40. And then I'm going to estimate that. I'm going to round it to 8.5 billion people. We weren't quite there. We're still, I think, only in the 7 billions. But things happened between 1975 and now that have slowed our effects of population growth. According to this model, when will the population reach 10 billion? Round to the nearest year. So I want the population, I want the output to be 10 billion. Right? This is already in billions. So I'm going to set 10 equal to 4 times 1.019 to the t power. I'm going to isolate the exponential part, so I'm going to divide both sides by 4. 10 divided by 4 is 2.5. The right-hand side divided by 4 leaves me with 1.019 to the t power. Now, if I have an exponential and the variable is in the exponent, I'm going to rewrite to logarithmic form. This tells me that t is the power, all a log is a power, to which I raise 1.019 in order to get 25. And if you have a fancy log base button on your calculator, throw it in there. If you don't have the fancy log base button on your calculator, you could use the change of base formula. Log of 2.5 divided by log of 1.019. All right, so those are L's. Natural log, logarithmic naturalis. All right, the natural log, when I put that in my calculator, I get approximately 49. But it's not the year 49. I can guarantee you there were not 10 billion people in the world in the year 49. I wasn't there, but I'm pretty sure, like 99.99% sure. 49 years after 1975, it wants to know when in 2024 we should have 10 billion people according to this model. Part C, according to this model, what was the world population in 1975? Remember, 1975 is when we started. That's a time value of 0. When t is 0, 1.019 to the 0 power becomes 1. 1 times 4 tells me the population, the initial value, our A value here, 4 means there were 4 billion people in 1975. I'd have to look that one up. I was alive then. I don't know. I can't verify that. I didn't count them. According to the model, by what percent is the world population growing each year? Our growth rate has to do with our base multiplier. The growth rate is always the base minus 1, because 100% of the population is still there. How much did we grow is the amount the base is over 1. So 1.019 minus 1 gives me 0.019. If I turn that into a decimal, I move my decimal 2 places. I lied, I'm not turning it into a decimal, I'm turning it into a percentage. The decimal moves 2 places, and I get a percentage growth rate of 1.9% growth each year. Oh, that was a lot, wasn't it? You got this. Let's talk money. Suppose that $2,000 is deposited into an account where the interest is compounded annually. This situation can be modeled by the function f of t equals 2,000 times 1.052 to the t power, where f of t is the value in dollars of the account t years after the initial deposit. All right, so whenever that was, we're counting t years since the deposit. In how many years, find t, will the money in the account double? Right? You want to make money. So the account doubles when the output is 4,000. Right? You initially invest 2,000, double that is 4,000. So we want to solve the equation 4,000 equals 2,000 times 1.052 to the t power. In order to find my t, right, in exponential, we have to isolate the exponential. Let's divide both sides by 2,000. I'll get 2 equals 1.052 to the t. I chose not to use parentheses anymore. Once I have the exponential part isolated, I'm going to rewrite in logarithmic form. T is the power, all a log is a power, to which I raise 1.052 in order to get 2. If you prefer the change of base formula, that's the natural log of 2 divided by the natural log of 1.052. And I use my calculator to evaluate that at 13.7 years to double. I have to leave that $2,000 alone for 13.7 years, and it's only going to double on me? I don't know. I might look for a better investment. According to this model, how much money will the account have in 10 years? Years. 10 years. T is years. Let's put a 10 in for T. 2,000 times 1.052 to the 10th power. $3,320.38. But how do you know if you're right? Like that doesn't seem like very much money. But remember, it takes 13.7 years to get $4,000. 10 years, I should have less than $4,000. All right, that seems reasonable. That seems like it's a possibility. According to this model, what is the earning interest rate? That's interest rate. That's the amount your money's growing by. So the growth rate, still base minus 1, because you keep 100% of your money, and then you add to it. 1.052 minus 1 gives me 0.052, and in percentage form, that's 5.2% interest. That's it for exponentials. Couple of applied problems there. Thanks for listening.